Hello again, let's pick up where we left off, continuing the Algebra Review Part 2. In this particular portion of the videos, we're going to look at fully factoring anything that is larger than a quadratic, some of our techniques for synthetic division, and that's something you will come across potentially in some of your functions in calculus. So the factor theorem, as a reminder, says that x minus k is a factor if and only if when you plug in that k value to the function, you get 0. Basically saying that factors and zeros go hand in hand. And we can use synthetic division to prove whether or not something is a factor. So when it says fully factor 6x cubed plus 19x squared plus 2x minus 3, given that negative 3 is a 0, it's telling you that negative 3 is a 0 or x plus 3 is a factor, and you want to factor this. So the way we're going to do this, as a reminder, using synthetic division, is negative 3 goes on the outside, and all of our function coefficients go on the inside. And then 6 comes down. 6 times negative 3 is negative 18. We add going down to get 1. And you multiply going back up. So 1 times negative 3 is negative 3. Add going down to get negative 1. Negative 1 times negative 3 is 3. And of course, the remainder represents exactly what you would get when you were plugging in that value to the function. So that means if something's a factor, that means your remainder when using synthetic division will be 0. And then the rest of the coefficients down below tell you what's left when you factor out the factor. X minus negative 3 is really x plus 3, and that leaves 6x squared plus x minus 1. We factored out something with an x from something with an x cubed, so our leading coefficient is x squared. Once you can get the expression, this function, down to quadratics, then you can use your old factoring techniques in order to determine the rest of the factors. So if we factor 6x squared plus x minus 1, again, we know that we need to multiply a times c. 6 times negative 1 is negative 6. So I'm really looking for the factors of negative 6 that are going to add to my middle coefficient of 1. This is factoring, which we did on the previous set of notes. So 3 and negative 2, which allows me to break apart my middle term into its two pieces. From there, I will factor by grouping. Ask myself what 6x squared and 3x share. They share 3x, leave x plus 1, 2x plus 1, excuse me. And the negative 2x and negative 1 share a negative 1 and also leave 2x plus 1. So my two factors here are 3x minus 1 and 2x plus 1. And this is, of course, factoring what was remaining over here. So the x plus 3 is still in play. So the fully factored form of this is x plus 3, 3x minus 1, and 2x plus 1. Now, the rational zero theorem says this is not a guess and check. You don't need to guess every number under the sun to figure out what could possibly be a root. Any potential root of this polynomial has got to, the numerator of the root, or 0, has to be a factor of the constant, whereas the denominator has to be a factor of the leading coefficient. For example, in this next equation, f of x equals 6x to the 4th plus 7x cubed minus 12x squared minus 3x plus 2, our p, our constant, is 2, and then the factors of 2 are just 1 and 2, whereas our leading coefficient, q, is 6, and those factors are potentially 1, 2, 3, and 6, which means all of my possible p over q's are plus or minus 1 divided by 1, 2 divided by 1, which is 1 and 2. Then we need to divide them by 2. 1 divided by 2 is 1/2. 2 divided by 2 is 1. We already have it listed. We don't need to do it again. 1 divided by 3 is 1/3. 2 divided by 3 is 2/3. And then lastly, we divide by 6. 1 divided by 6 is 1/6. 2 divided by 6 reduces to 1/3, which means it's already listed. So the only actual factors we could have here are plus or minus 1, 2, and all of those potential fractions. So we can test any of them with synthetic division. From the looks of it, I think we can go ahead and try 1 just to see if it will work. We'll put 1 on the outside. Put the coefficients on the inside, 6, 7, -12, -3, and 2. 6 comes down. 6 times 1 is 6. 7 plus 6 is 13. 13 times 1 is 13. You add going down, get 1. 1 times 1 is 1. -3 plus 1 is -2. -2 comes up. And then we get 0. So this demonstrates that 1 is a factor. So we know that we've got x minus 1 as a factor, and then 6x now cubed plus 13x squared plus x minus 2 as potential remaining factors, or the function that can produce more remaining factors. Now, because 1 already worked one time, it could work again. If you were to plug it in here to try it again with the new coefficients for what remains, it does turn out that it doesn't work. So we should try something else. I'm going to vote for -2. You should always, though, check the things that worked one time before you rule anything out. 6 comes down. 6 times -2 is -12. 13 plus -12 is 1. 1 times -2 is -2. 1 plus -2 is -1. -1 times -2 is 2. And we get, again, 0. So if -2 is a 0, that means that x plus 2 is a factor. So we've got x minus 1. We've got now x plus 2. And what remains is that from down here, 6x squared plus x minus 1. Now, we can factor that using our normal techniques. However, if we look at the previous problem, it's the same 6x squared plus x minus 1 that we had, say, up here. So I'm pretty comfortable saying that we can follow the same steps to get the rest of the factors. X minus 1, x plus 2, 3x minus 1, and 2x plus 1. Now, these are the factors, but if it asks for the zeros or the roots, you need to take each of your factors and set it equal to 0. So if we were asking for the roots, x minus 1 equals 0, x plus 2 equals 0, 3x minus 1 equals 0, and 2x plus 1 equals 0. That leaves you with potential zeros of x equals 1, x equals -2. Here we get x equals 1/3, and x equals -1/2. You'll notice that all of these came from this original list of potential roots. So it does reinforce the fact that this works. Now, on this next page, I have a rather large polynomial where it wants all solutions, so you'll factor it and find the zeros. But I want to leave this one to you to practice so that you can get comfortable with doing this. I imagine you have done it before, but I want you to do it again just in case. And we will finish these notes in the next video.